So, welcome to class 12 of topics in power electronics and distributed generation. In the last class we were talking about grounding of distribution systems, and we saw that in the example that we were discussing in class that there is a possibility where you might have a upstream breaker in your circuit opening when a DG is when a downstream DG is still connected to the system, and there is a possibility that this connected DG may operate and continue to excite the feeder even when upstream breaker has opened. And this particular situation of a upstream device opening and the rest of your distribution system operating being excited is called a unintentional island, where for some unintentional reason an upstream breaker opened, but the DG, if it can actually stay connected and provide power to the loads on the system, it will continue to actually excite the feeder, and we will see that islanding is an important issue when we look at distributed generation. So, when we talk about islands in a distribution network, in geography an island is a land body which is disconnected from the mainland, separated by water. So, if you look at electrical system, electrical island is essentially a small part of the distribution electrical network in the distribution system. And this is the smaller network is disconnected from the main grid due to a open circuit. Okay. And a typical cause of the open circuit might be a upstream breaker opening or a fuses blowing. It can be just the wire physically breaking. So, there can be a variety of reasons why you might result in an island. Common situation would be a breaker opening. Okay. And electrical islanding situation, it can be of two varieties. One is you have an intentional island, or you can have an unintentional island. Okay. So, if you look at intentional island, the reason why one would typically have an intentional island is for a reason of power quality. Okay. And the idea is you open say a breaker which connects to the main grid, and then your source can actually feed a local load when there is poor power quality in the main grid. Okay. So, you want to isolate yourself from the main grid and continue to feed higher quality power to your load in a dedicated manner. So, there might be reasons why you intentionally operate as an island. So, the question comes, what do you mean by power quality, or it is more often measured by what do you mean by power quality being poor as seen by the load. Okay. So, a load seeing poor power quality from the supply can be for a variety of reasons. The primary reason being that there is no supply at all, there is a outage and you want to actually feed your load. So, that is a primary reason. Okay. If you are having electric supply, you expect your voltage line to neutral voltage to be 230 volts, some nominal voltage. Typically a band around the nominal might be acceptable. You might have your voltage say plus 10 minus 20% band around nominal might be considered acceptable power quality. If you go beyond that, you may want to disconnect rapidly. You might have say voltage imbalance. I mean your voltages might be close to nominal, but your phases may not have equal amplitude voltage, or there may be some phase shifts. It depends on the type of load. I mean say for example, if you are feeding single phase loads, then the imbalance may not be a major thing, but if you are feeding say induction machine load, then even imbalance of 3% would be considered unacceptable. Okay. I mean you can see why say 3% might be considered unacceptable. A typical induction machine has leakage inductance in the range of say 15 to 20%. So, a 15 to 20% imbalance would mean that even at no load, your current drawn imbalanced current drawn would correspond to almost full load when there is a 15% imbalance. So, if you are having something like 3% imbalance, it means that you are having 20% of your current coming in because of your imbalance. So, you might have a service factor of 20% on your machine. So, that might be the maximum that you can tolerate on a continued basis. So, your imbalance percentage is typically much tighter than what is your acceptable voltage amplitude. Also your frequency might be outside what is your acceptable range. I mean depending on what is the process that you are trying to do. You might be trying to do some speed control, there may be some machines which are susceptible for mechanical resonances. Say if you are having something like a computer power supply, it might be able to accept a wider range of frequencies, but if you have fans, mechanical loads, you might need a tighter range of frequencies. Say locally we might say 48 hertz to 50.5 hertz might be considered as something which might be acceptable. If you go outside that range, you might want to disconnect, again depending on your load, what is expected at the load, okay, and your nominal frequency is 50 hertz. Another thing that you might say would be a situation of poor power quality is when you have harmonics in your load, you have distorted waveforms. People measure harmonics in waveforms in terms of total harmonic distortion. So, acceptable THD level for your voltage might be less than 2%. So, you want to make sure that your voltage that is being supplied to you is not very highly distorted. Okay. Again it depends on how sensitive your load is. You might have some tighter requirement for very sensitive type of load. You can have transient effects which would also affect power quality. An example is a short term duration of voltage amplitude increasing, or a short duration where the voltage dips. This is a sag or a swell. You might have notches in the waveforms if you have equipment such as thyristor power converters connected to your point of common coupling. You can have flicker in your load. If say someone is operating electric arc welder in your same street as where you are living, then chances are you will see a lot of flicker in your voltage. That so you can see that as lights that are glowing brightly and then it becomes dim, again glowing brightly. Some people are extremely sensitive to variation of light intensity. So, for many of these power quality reasons, you might want to intentionally disconnect from the grid and open a breaker and then feed your local load from a DG, so that when the power quality is poor, you have your critical load being fed from your DG. When the grid power quality comes back to an acceptable range, you would then close the circuit breaker and operate in a normal condition. And the common systems that use such a property are UPS systems, gensets, they all operate in this particular manner, where you are addressing poor power quality by adding such components. You can also have a situation where to address power quality, it may not be just the your own facility breaker that you open. You might for some reason be capable of opening a breaker at the network and providing poor power, improved power quality on the feeder itself. It depends on whether your distributed generator set has the capability to provide that level of power, both real and reactive. Also whether it can operate stably with such a big network, wider network. You could also have other technical conditions which may need to be satisfied. Is this DG capable of clearing faults in your neighboring load? There may be non-technical issues, such as what is the economic benefit of providing power to your neighbor, or there may be legal questions like who owns different aspects of the system. The utility might own the lines, the one entity might own the DG, another entity would own the next load. So, there are a number of issues to be addressed, where if you are trying to operate in as a intentional island on a broader sense, and people refer to such situations as microgrid at the distribution level, not microgrid at within a small facility, but microgrid at the distribution level. Okay. So, if you look at then the other situation where you can have an island. So, what we discussed so far was when you have an intentional island, you can also have the situation where you have a unintentional island, and the unintentional island, as we just saw in the example that we discussed, it is not because you intended to actually open an upstream breaker, but it opened for a variety of reasons, and for some unintentional reason now your DG is exciting the feeder, okay, the common network, the feeder network, and it can lead to a variety of problems. Okay. And will and even for forming an unintentional island, you have requirement that the DG that you have should be capable of providing the power for your neighboring loads. Okay. So, if your total load on the feeder is of the order of megawatt and your DG is 1 kilowatt, obviously it cannot form a island. So, you are talking about capability of your DG and your load to be similar, both in terms of real and reactive power, okay, requirement, being able to match that. And for the unintentional island to be operated in a sustained manner, you need to have a stable operating point of the DG and the load. Okay. So, there are a variety of reasons why unintentional island is not desirable, and the primary reason is safety concern. Okay. Typically when you open a upstream breaker in a distribution system, the assumption is whatever downstream of it is de-energized, which means it is potentially safe to go and touch. Whereas now you have a DG system, you open an upstream breaker, now potentially the downstream system is still energized. So, if a person, a lineman goes to repair the downstream system, he can potentially get shock, he can get electrocuted. So, safety is a major concern. Okay. So, so, you can address this issue in a variety of ways. You can try to have live line type of repair. When you go to larger transmission systems, you can do repair of the transmission system components without de-energizing the line using people in Faraday cages, etc. But that makes it a more complicated operation, it is more expensive. Safety is a big concern when you are having possibility of DG source forming a unintentional island. Okay. Also, you can damage the utility equipment in an unintentional island, and we saw that the faults may not clear, the capability of the DG to provide fault current to trigger a protective device might be lesser than the main grid. So, you might have the change in protective coordination settings as we saw in our example. You can have sectionalizers that open under load. You also have the possibility of what people refer to as ferroresonance. So, on a distribution feeder you would have capacitors, could be for power factor correction, and then when you are connected with the grid you have those capacitors and your magnetizing branches of your transformers, etc., which are connected in parallel to a stiff grid, which prevents your voltage from going to be different from your nominal value. And when you connect a DG source which might have much higher impedance and you disconnect the voltage source, the chances of resonances could be high. So, the resonance between your magnetizing branch and capacitances might be power factor correction capacitors, or it can be capacitances of cables, can actually lead to ferroresonance, and you can see highly distorted waveforms with sharp peaks, and that can damage utility equipment. Okay. You can also damage the distributed generation source itself, because you can have overloading, because you are trying to carry a wider set of loads of the entire feeder. Your frequencies might drift outside nominal values. Also, you have something that is a possibility is that is out of phase reclosing. And we will see that out of phase reclosing is actually an important issue when we consider a situation of damage. It can actually damage the DG, it can damage other customer equipment, it can also damage utility equipment. And such a situation can arise where, say, you have a upstream recloser, and we look at an example where say the upstream recloser has off duration of say 5 seconds. So, we will look at an example where your grid frequency is 50 hertz, and you assume that after the recloser opened, then the loads with your DG in the island the frequency shifted to some other value, say the the system frequency shifted to f of the island, shifted to say 49.9 hertz after disconnection of the main breaker, and the recloser say stayed open for 5 seconds and then it tries to reclose. Okay. So, we will look at what would be the phase of the voltage on the grid side and the phase of the voltage on the island when the recloser is reclosing. And to determine the phase of the voltage, you have your delta f, is 0.1 hertz, and then you look at what is the phase shift that occurred in this duration. Your delta shift in phase is delta f into T off into 360 degrees. So, this is 0.1 into 5 into 360. So, this is 180 degrees. So, you can see that the waveform would be a sine wave like this over here. It could be, it will have the opposite polarity. So, when the recloser closes, it is trying to introducing a abrupt 180 degree phase shift in the voltage that is now getting applied to the system. So, you can see that in any electrical system, even a nominal direct online start will cause a large inrush. Now, you are having a almost like a 180 degree phase shift. Your currents that can flow in such a situation is much higher than a normal say direct online start, and you can have severe repercussions. You can, if this is a synchronous machine type of then you could potentially damage the DG source. If there are fuses on the distribution system, the current that it might draw might be large enough to damage open the fuses. And what we will see is that if you have a neighboring load, when the voltage over here drifted for 5 seconds and became out of phase, then essentially the phase of your flux vector in your machine is also following that particular voltage in the island. So, now you have induction machine where its induced magnetic field is in one polarity, and the voltage that is now being applied from the grid is 180, is trying to create a magnetic field 180 degrees out of phase. So, the current that flows into this inrush into the machine can be as high as twice your current that you would see in direct online start, or even higher because of saturation effects. So, you can possibly have things like 10 per unit peak torque that you would see on the shaft of the machine. Potentially you can actually damage the shaft can actually crack open. So, there can be extensive damage, now not just for the DG, but for all loads that are connected on the feeder. So, you can see that this is a very important consideration when you have a DG system. So, the other customers and if you are applying a step voltage of twice the peak value, you can have resonances with parasitic capacitances on the line. You can get resonant over voltages that go up to 4 per unit. So, that is really high over voltage, and if you end up damaging the neighbor's electrical equipment, then there is a big question of who is liable. Okay. So, if you look at a typical electrical system, the cost of all the equipment that is connected to the electrical system, you might have very expensive process equipment, you go to data center, you might have lots of expensive computers. So, the connected loads would have much higher value than the original electrical system, which is actually providing the energy feed. And if you end up damaging all the loads, then there is a severe liability issue, and typically your electricity service provider takes insurance that they would cover in case they provide extremely poor service, that your equipment is damaged, they are liable to actually pay you for the damage that they have caused. So, now if DG is doing this, then the question is, who is responsible? Is it the DG owner, is it the service provider, or should the customers themselves be taking the liability? So, the issue of how to deal with electrical island, especially the unintentional island, is important concern in DG systems. So, if you look at the example that we saw over here, here we looked at a recloser where your T off was is 5 seconds, and the amount of duration that your T off can have can vary. I mean, you can have fast reclosing, you might have slow reclosing, and people consider 2 seconds to be a reasonably fast reclosing. So, if you look at standards such as IEEE 1547, it says that distributed generation source should disconnect before 2 seconds after opening of a upstream device, and the reason is that before the upstream device recloses, you need to be able to detect that something upstream has opened and de-energize the DG, so that you do not have possibilities of out of phase reclosing. Okay. So, minimum T off so you need to detect a situation of an unintentional island in a fairly short time frame. You cannot use algorithms which might take tens of seconds or minutes. You need to be able to detect that something like this has happened in a second or two, okay, or faster. So, if you want to detect a situation of an unintentional island, people have employed methods. People call it anti-islanding algorithm. Essentially, what detects a situation that there has been an unintentional island, and the types of anti-islanding detection methods can be thought of as being passive, or it can be active, or it can involve signaling or communication. Okay. When you look at passive methods for anti-islanding, what you are essentially doing is you are measuring your voltage and current at the terminals of your DG device, and or at the interconnection point of interconnection with your main grid. You are measuring it through potential transformers, CTs, into some protective relay, and you decide on whether to open or keep the interconnection breaker. You decide on whether to keep it open or closed based on the decision of the algorithm. Okay. and it typically does not directly interact with your DG controls. And that is one of the reason why it is called passive, because it does not actively try to shift the control action. And the passive methods are not always 100% effective, if it is, especially if it is based on pure voltage measurements. And or you might have restrictions on how the DG is operated, which will prevent and how the loading is being done in the facility. So, there might be restrictions on operation. Okay. And if you are looking at the voltage, essentially pure voltage based methods might be, you might be looking at if the voltage goes too high or too low, then potentially there might be a islanding situation, or you might be looking at under or over frequency, or you might be looking at the direction of power flow. So, we will look at some of these methods of passive and anti-islanding. Before that, we will also discuss some of what would constitute active and anti-islanding method. So, this is based on adjusting the distributed generation source operation based on your actual measurements. Okay. And the idea in this particular case is that you destabilize the island, so that the operating point that you get when you disconnect an upstream device would not be stable, and because your operating point is not stable, it means that your voltage amplitude or your frequency would go outside, it would go outside what would be a nominal range, and the fact that your voltage or frequency went outside the nominal range would be used to actually open your interconnection device. Okay. And if you look at the method of active and anti-islanding, it makes use of measurements, it makes use of active controls. So, its reliability would be a little bit less compared to the passive method. Ideally, if a passive method can operate reliably, that would be a better method, because active method is now using not just your detection, but also now active controls. So, you could think of it as being slightly less reliable, but the chances of detecting an island might be more in the active method. Okay. The third method is communication based methods or signaling based methods. In the traditional transmission systems, people have used pilot relays to transfer information from one point to the another point to make better decisions. So, you could use information maybe from the substation to the DG to inform whether a substation breaker is open or whether some feeder need to be de-energized. So, you could make use of explicit signaling or communication. And in this case, now you need an additional channel rather than just the power lines, you need now a communication channel to be also available. So, the cost can potentially be higher when you want such systems to work. Also, reliability of the communication channel may not be as high as the underlying electrical network. So, you have reliability concerns. To address some of the cost issues, people have looked at methods like power line carrier communication methods to see whether the power line itself could also carry this information on the status. So, people have looked at a variety of such methods to see whether you could have explicit signaling based methods that can be effective. But again, in this particular case, reliability is a concern, because in this case you have coordination between multiple agencies for some algorithm to work. You have to have coordination from your utility, which is sending the information, then coordination at the DG side, which is taking that information and using it to open a breaker. So, that becomes more complex a problem rather than one entity making the decision by itself in a reliable manner. Okay. So, we just mentioned that the effectiveness of an anti-islanding algorithm, it may not be effective at all times, especially in the context of a passive method, and you might have a range of values where the method may not work well. For a range of parameters or a range of system values where the islanding method may not function in an effective manner, and the range of region where the region of the parameter space where the islanding detection may not be effective is called a non-detection zone. Okay. So, a non-detection zone and the objective of a good anti-aliasing algorithm is to make the size of this non-detection zone to be 0. So, ideally it should be 0, which means that it would be a very good anti-aliasing algorithm. So, what we will do next is to look at a model of your feeder with your distributed generation source, so as to look at the situation of passive anti-aliasing detection on that feeder. Okay. So, we will look at what it means for this simplified description of the feeder. So, what you have over here is the upstream grid modeled as a voltage source. This is essentially what comes from your substation, and you might have a breaker, upstream breaker modeled as the switch S1, which can open. Okay. All the loads on the feeder are modeled as it's modeled as a RLC, a parallel RLC load. Typically you might have your real power consumed by your R load, reactive power being drawn by L, your transformers, whatever components, machines, etc. And you might have power factor correction capacitors, etc. on your feeder. So, you could think of your overall load to consist of a RLC equivalent network, and you can model your distributed generation source as something that injects power and reactive power, and we will assume that the reactive power that is injecting is 0. It is operating under unity power factor, trying to inject power at unity power factor at its point of common coupling. And we will look at a situation where the amount of power that is being drawn by the load matches well with the power that is being supplied by the DG. If the Q reactive power from the DG is 0, it means that the balanced reactive power is the difference between the reactive power drawn by L and C, and if the feeder is well compensated, it means that your Q of the load would be almost 0. Okay. So, if there is any difference between what is being drawn by the load and what is being supplied by the DG, that is essentially delta P and delta Q coming in from your main source, which is your main grid. So, the problem can be simplified as when the switch is closed, your main grid sets your voltage and frequency seen by your RLC load. Then when the switch S1 opens, there might be some deviation in the voltage and frequency seen at this particular load, and can you operate switch S2, which is downstream, by looking at this voltage and frequency? Can you operate the switch S2 to actually disconnect the DG in response to the changed value of voltage and frequency? Okay. So, that is essentially the anti-aliasing problem. If S1 opens, under what conditions can the anti-aliasing algorithm determine the that such a situation has occurred, and it needs to open S2 as a result. So, so the other assumptions over here, that the DG is capable of providing power, that whatever power is being drawn by the your load. The other thing is that because your DG is providing power at unity power factor, then the assumption is you have very good reactive power compensation. Okay. So, the feeder is well compensated. So, if you look at the first situation, you have if V square by R is your load power. So, this implies that your delta P is P of the load minus P of your dG is 0. So, the second situation is if your feeder is well compensated at 50 hertz, then your omega is, which is 1 by root LC, would turn out to be 2 pi times 50. So, if you have a parallel resonance circuit, if your resonant frequency is 50 hertz in a parallel resonance circuit, whatever you draw would be in phase if there is a resistive load, or it will not draw any current if there is no resistance load, which means that your reactive var of your capacitor is exactly balanced by the vars of your inductor. Okay. So, your QL is QL of your inductor is and you can calculate both of this would turn out to be equal to V square divided by square root of L by C. So, if you look at your delta Q that is being drawn from your source, this is equal to Q of your load minus Q of your dG, and Q dG is 0 and QL is equal to QC. So, this is equal to 0. Okay. So, essentially if you look at conditions 1 and 2, what you are going to have in the ideal situation is that you are going to have sustained LC oscillations even after opening the circuit breaker. Okay. So, the third aspect that we will look at is what is the quality factor of this resonance. And your resonant frequency is 1 by square root of LC. So, it turns out that your QF is R divided by root of L by C, and you also know that omega is 1 by root LC. So, you can substitute for this, you will see that essentially QF is equal to Q of your inductor divided by your P load is equal to Q of your capacitor divided by. So, in a situation where if QF is high, what this implies is your P load is less than your Q of your inductor or Q of your capacitor. It means that your system response is going to be dominated by your LC oscillations, and your loading, even if there is some level of loading mismatch, your exponential term, which is essentially your damping term, may not be the dominant term in your overall response in the time frame required in your analysis. So, for the anti-islanding test, what we will look at is a situation where QF is greater than or equal to 1, and essentially what you are looking at is if in the ideal condition, if you are opening the switch and your delta P and delta Q is close to 0, what it means is that after opening the switch there is almost delta P and delta Q is 0. It means that the current flowing through the switch is 0, and opening the switch will not cause any disturbance. Your V and F will continue to be where it originally was, which means that any method that's measuring your voltage and frequency to open the circuit breaker of the DG would not be effective. So, having small values of delta P and delta Q, it would mean that method with pure voltage or frequency measurement would not work. So, you need to have some mismatch in your delta P and delta Q for just pure voltage based methods to work. In our next discussion on islanding, what we will do is try to look at the threshold of your voltage and the threshold of your frequency, and look at how that relates to how much delta P is there, how much delta Q is there, to look at what is the relationship between essentially you can think of delta P and delta Q to be aspects of your non-detection zone, which can again be reflected in terms of what your R, L and C parameters are and relating that to the DG, and we will try to see how that can be used to set voltage and frequency thresholds to determine a situation of an unintentional island in a passive manner. Okay. Knowing well enough that it would not be 100% effective in a situation where you have a feeder where your feeder load is 1 megawatt and your DG is also providing 1 megawatt, there is a potential that such a method may not work. But if you would be able to say, if your now feeder is 1 megawatt, can I introduce up to half a megawatt of DG and still be able to detect a unintentional island. Okay. So, you could ask questions like that with such an analysis. Thank you.